Okay. So last time we learned about linear regression algorithm. Okay. So this is the simplest form of the regression. Okay. And we learned the gradient descent algorithm that can optimize their parameters, which is the W and B. That is the parameter for this linear regressor. Okay. And this linear regressor, they are called as linear regressor because they are having this form, Wx plus b, which is the linear equation. Okay? This is the simplest form, and they are doing the regression task. Okay, and and also I also explained that this linear regression can be, straightforwardly extended to the multivariate case, okay, by just making the input to the array, to the vector, okay. And I also explained the difference between two libraries, the NumPy and PyTorch. NumPy, that's the library that is, that is helping us to implement the array in the Python. Okay, so we can implement the linear regressor using the NumPy. Also, the PyTorch, this is the library that is developed by Meta, and that is helping us to implement some deep layers easily. Okay, they are actually helping us to easily calculate the gradient in the entire architecture, and also they are also providing GPU usage. They are providing easy interface to use these GPUs. So I will also explain about this later. So when training the GPUs, you may already heard that OpenAI or other big companies that is doing the AI, they are building data center and also the GPU clusters to train their AI. Okay, so nowadays GPU that is very essential to train this deep architecture because they are very big and they are having many parameters. And without this GPU, we cannot train those big architectures in feasible time. Okay, so using these GPUs, that is very important for deep architecture. So I will explain further about this later. Okay. Anyways, they are providing easy interface for this. So we already seen that their calculation of gradient is very easy. We can call just one line of code, low start backward, okay? Then they can automatically calculate all the gradient inside the graph, okay? We already learned about that last time, okay? And also last time, I think there was a confusion here, so I will clarify that. 근데 에어컨 저기 온도 좀 다시 볼 수 있나요? 좀 덥지 않나요? Okay. Last time, I think there was some confusion in this slide, so I want to clarify that. So previously, the error, there was a confusion in their name. So this is not error, but this is some intermediate variable. So we just want to calculate and save this in this errors variable, okay? But our final loss is here. This is the loss. So our loss is, as I mentioned, the distance between our predicted value. This is our predicted value, right? From the regressor, linear regressor, right? And this is our ground truth, okay? Their distance, we will measure their distance in the Euclidean distance, okay? And actually, that can be found, this is the formula for that. because W and Y, they are in the vector form, so we usually, notate that like this, okay? But you can also write it in this way, okay? That is the Euclidean distance. Anyways, uh, in this code, they are first finding these errors, which is the just difference of them, the predicted value and ground truth, and then we apply square for this, okay? And then summing all and multiply 0.5, okay? So this is our loss, okay? Or you can call that as the error, okay? The error between predicted value and ground truth, okay? So in the regression task, as I told you before, um, this is our final loss, okay? So that is actually same thing I mentioned here, okay? Mentioned here, right? Okay. So if this is array and vector, and for all the input, we can just calculate this. So because of that, we are summing. This summing is for summing over all the training samples, okay? So actually, if there's I sample, uh, n samples and training samples, then we have to sum over this n samples, right? This is our final loss, okay? But the thing we have to calculate is these two values, okay? So to use this gradient descent, okay, we have to calculate these two and update W using this value and update B using this formula, okay? Are you agree with this, right? So, we have to calculate this, okay? And then we have to implement this to implement this formula, okay? And here, these two lines of code are implemented for calculating these two values, okay? And how to calculate that is, we have to get the closed form differentiation for these two values. So if we differentiate this loss or the error with respect to W, then it would be like this. So 1/2, and if we, differentiate this with respect to W, and there should be some over n. And then if we, so this is a bit narrow, so I will write it in the bigger space. So, sorry. And then because W is variable and all others are constant, so if we differentiate this term, then xi will be come out. Okay, I agree with this. This should, you have to learn about this in the calculus course, maybe, right? So are you agree with this, right? So if you write it in the code, then that looks like this. So this is removed, and x dot transpose, this dot t is the transform, transpose, okay? So because this is vector, you have to transpose that and apply the dot product between, this is error, we calculate here, right? This is error variable, and this is x dot t is here. So this becomes the dl, differentiation of loss L respect to the W, okay? And also you have to calculate dl dB, and that would be y, but if you differentiate this respect to b, then just one is outcome. Okay, so here you just use the error, this variable by summing over all the samples. Okay, so I mean when implementing, anyways, this simple linear regression using the NumPy library, you have to calculate this differentiation by yourself. Okay, and have to implement that formula, that closed form solution for the differentiation in your code, and then use that to update the parameters. Okay. Okay. So this is the NumPy things. But as we see last time, if you use the PyTorch, you don't have to calculate this closed form solution for the gradient. Okay. Instead, you can just type, I mean, how these inputs, the B, W, X, and Y are connected via operator, okay? And how to calculate the final loss from them. Then inside the PyTorch, they are building some graph, how they are connected, okay? This is some examples, okay? How they are connected inside the PyTorch. And this type of graphs are constructed, okay? And then if you pull this load step backward, then they already know which variables are connected in which order, okay? And then they can track it and calculate this automatically without calculating these two forms in the closed form solution as the closed form solution, okay? And you may learn about, maybe in calculus course, you may learn about the how to calculate this gradient for arbitrary function. There's some algorithm called as Newton's algorithm or other algorithm that can approximate the gradient for arbitrary functions. There's some algorithm already. So that's called as numerical way for calculating the gradient. So, I mean, rather than calculating the gradient with closed form solution as humans does, right? In computer, they can also approximate the gradient without calculating the closed form solution of the gradient, okay? That is implemented in low-step backward, okay? So, I mean, using that algorithm, this PyTorch library can approximate gradient for all the variable inside the graph, okay? So you don't have to worry about how they achieve this, okay? And because of that, if we use the PyTorch, the implementation becomes very easy, right? And even more thing I want to point out is, if this, how to say, the forward functions are changed, you have to calculate your gradient every time the forward functions are changed, okay? But if you use that numerical algorithm to calculate the gradient, that algorithm is not changed, okay? So you can apply the same algorithm that can approximate gradient regardless of the forward function, okay? But you have to re-implement this gradient closed forms for the gradient whenever your forward functions are changed. So that's another merit of using the PyTorch, okay? Anyways, the implementation becomes very easy when using the PyTorch. You have to remember that, okay? And also we also check, so this is a big difference between the implementation via PyTorch and NumPy. NumPy, you have to calculate the closed form solution for the gradient by yourself. But in the PyTorch, you don't have to do that. This load stop backward automatically calculate all the gradient inside the graphs constructed, and you don't have to care about their gradient. Okay, and also even we can also simplify this type of code further. Okay, so I already showed that. So in this code, I already explained that we can also simplify the remaining PyTorch code. Okay, so without coding their parameters explicitly, we can we can make some net variable that can specify their entire I have to say bigger models. And then using that, we can also optimize code, okay, further. I mean, we are not wanting explicitly reveal their parameters, but want to, how to say, encapsulate their variables inside this type of functions, okay? So that is more easy to use, okay? Okay. So are you guys understanding this? Okay. Any questions for this? This is actually the very important part of this course. Okay. You have to fulfill your maybe assignments using this code. Okay. So understanding this code is actually very important. Okay. And that is linear regression. And this is the example code for implementing linear regression using the PyTorch. But from now on, you will see the exactly same code could be used to train more complex architectures, which is called as MLP, multi-layer perceptron. Okay, so we normally call it as MLP. Okay, so this multi-layer perceptron, so you can interpret this perceptron as some network. Okay, we call this type of things. We will call this type of things that is having input and output, and having some layers, having this type of operator in between the input and output. We will call that as the network. Okay, and perceptron is so you can think this type of architecture. So this is kind of different name of the network. Okay. And multi-layer perceptron is called as multi-layer perceptron because it has multi-layers. Okay. And you can, this is the multi-layer perceptron that is inspired from human brains. Actually, human brains that is composed of neurons, which is the basic block. Okay, and you can interpret that basic block as the linear operator. Okay, so this was the linear operator, right? Okay, we will call this as the linear operator, linear layer. Okay, we will frequently use this linear layer. Okay, the linear regression algorithm, they are having this as the entire block. Okay, but we will stack this type of linear layer to constitute more complex networks. Okay, and you can think this linear layer, which is the simplest form of the layer, as the neuron. Okay, in the human brain. Okay, so human brain neurons are the basic block, and if they are stacked, and they can represent some complex signals, right, in the human brain. Okay, that's similar to that. So the how to say the AI researchers in the early ages, they are inspired seeing the brains. They realize that the simple neurons are stacked, and they can represent some more complex how to say signals. Okay, so inspired from that, they are proposing this type of multi-layer perceptron. Okay, that is composed of basic linear layers, but by stacking these linear layers, they are expecting that more complex signals can be represented, okay? And as I told you, maybe in the last of previous lecture, their formula looks like this. So at the first, they are stacking the linear layer having W1 and B1 as parameter, and then apply some sigma, which is the layer, some layer, and then apply another linear layer having this as the parameter, and apply sigma again, and then apply the third linear layer having this as parameter, and apply sigma to get y from the x. Okay? This is the structure of the MLP, okay? But you may question, you may ask why sigma is required here, okay? Regarding the sigma, I will explain that later, but let's assume there's no sigma in this formula, then you can simplify if there is no sigma in this equation, then we can simplify the right-hand side as like this, okay? And this becomes this part becomes W, and this part becomes the the scalar value B, okay? And you can realize that without the sigma, the entire big structure having three consecutive linear layers, this can be converted to a simple linear regression layer, okay? So the researchers become to realize that we have something that can prevent this type of reduction, okay? So to do that, they are applying the sigma function, okay? And usually we use some sigmoid, tangent hyperbolic, or ReLU, or other functions. And their common, common characteristic is their functions are nonlinear. So nonlinear means they are, meaning that they are not straight line, okay? So sigmoid, you will learn about that later. It has some values like this, okay? And tangent hyperbolic, that's also having this type of graph. ReLU, that is also having some nonlinearity in x when x is equal to 0. Okay, sorry. So this type of nonlinear functions are applied in the middle of the linear layers, okay? But thanks to these nonlinear functions, we can indeed have the nonlinear functions, nonlinear structures, even though they are mainly composed of the linear blocks. Thanks to intermediate nonlinear layer, we can secure the huge nonlinear layers, okay? And also, I will explain about this differentiability later, okay? And also, now we will train this MLP, okay? Similarly, what we did for the linear regression task, okay? And this is our new predicted value, right? And this is the ground truth for that. And we are having n training samples. We can, define the error or the loss in this way, okay? I agree with this, right? And we can apply the same gradient descent formula to update all the W values and all the B values, okay? And this epsilon is small scale scalar value. And anyways, we have to first calculate this gradient. And then if we apply this gradient descent algorithm for each parameters, then we can learn all the parameters inside the NLPs. Okay. Okay. That is the multi-layer perceptron. But before explain about this slide, I will show you the code for training these MLPs using the PyTorch code. Okay. And here, this is the data generation code. Okay. So we will set 1,000 training samples, and we will set 10,000 iterations for the training. Okay. And for given random x value, we will make their ground truth using this nonlinear formula. Okay. Y is equal to x squared plus 3. Okay. This is the nonlinear equation. Okay. And this is the network architecture for the MLP. So this torch.nn.sequential, this function means we will sequentially stack the layers inside this argument. Okay. So we will first stack linear layer, and this is one of the sigma function, sigma layer. And this is another linear layer, and stack sigma, linear layer, sigma, linear layer. Okay. So this is the definition of the network variable. Okay. Previously, for the linear regression task, we only use this torch.nn.linear, one layer of linear layer. Do you remember? So previously in this code, for the net architecture, we use just one line of linear layer, okay? But here when implementing the MLP, we sequentially stack multiple layers, linear layers, using the sigma function in the middle, right? Okay. And this becomes the entire network architecture. And using exactly same code as before, using the same loss function and same gradient descent optimizer, and using the same iteration, we will train this net architecture. Okay. Okay. And here, what they do is first they initialize all the variables gradient to 0 and calculate the output first, the network's output first, and calculate the loss, okay, loss for their predicted value and their ground truth y. They calculate loss, and using this one line of code, they calculate the differentiation of final loss respect to their intermediate parameters. Okay, by calling this command, you can do that. And then by calling this, you can update each parameters using gradient descent formula. Okay. And you iterate it for maximum number of epochs we specify here. Okay. Are you understanding this code, right? Okay. But I mean, one important code are missing here. So here, actually, I didn't explain how this X and Y data are, I mean, no. Here is also contained. Sorry about that. X and Y are already generated here. Okay. So, I mean, if you execute this entire code in the Colab, that will work. Okay, actually. So this is, I mean, explaining each line of code. And this is visualizing losses for each epoch. So each epoch losses, it is the empty array, but we are actually appending it using the loss for each iteration. So at the first, this is the epoch or iteration number. Loss was very high at the initial iteration, but you can see their losses are gradually reduced. Okay, loss means the distance between predicted value and ground truth. And I mean, the meaning of loss reduction means our predicted value is becoming close to the ground truth as epochs go. Okay. And indeed, for this is the code for doing some testing. You train the net architecture using the code in the previous slide, okay? And after getting the net, which is trained for 10,000 iteration, we will also generate the testing samples for that. So we will generate 5 number of random value for test input X, and then we will generate their corresponding ground truth using the same formula as before. And you will input your testing data to the net architecture, which is trained, okay? And this is our predicted value, right? And if you print those two, you can see this is the ground truth and this is the predicted value from the network, trained network. Okay, they are not same. I mean, they are not exactly same, but you can see their scales are having similar trend. Okay, so this is indicating that the net architecture is becoming to mimic this function. Okay, are you guys understanding this? Okay. So, I mean, we only stack the linear layers, okay, which is not representing some nonlinear equations. So, this is the equation for the straight line, okay. This linear equation only can only can explain the data lying on this straight line, okay? But by stacking this linear layer multiple times and using some nonlinear sigma in the middle of the linear layers, we indeed can model some, we indeed can make them mimic some nonlinear functions, which is the quadratic equation, okay? Okay. So are you guys following this? Okay. And then I have to, so using the same line of code by just changing this net architecture, we can now train this complex network. Okay. Even you stack more layers, more nonlinear layers that can be trained. Okay. Okay. Uh, and now I will explain about how the gradient values are calculated inside the, inside the graph. Okay, so I already told you when we build, when we code in the PyTorch, okay, when we code these things, the forward rule, which means how the final loss function is generated from the initial variables. If we code that inside the PyTorch, this type of graphs are constructed that can, connect the variables using the operator to calculate the predicted value y, and using the ground truth y, and eventually they calculate the loss. Okay, so the final output is loss rather than their predicted value. Okay, inside the PyTorch, they make this type of graph, and thanks to that, if we call the loss stop backward, only they can track all the variables connected to the loss and automatically calculate the gradient. Okay, but I will show you. Differentiation of this module. this simple module is rather simple, okay? But calculating, for example, this might be the final node, might be the loss function, okay? And we have to calculate the final node, we have to calculate the gradient which differentiate final node respect to the initial node of the graph, okay? And for each part of this graph, uh, to do that, I mean, for each part of the graph, this type of node, they have to have their, how to say, uh, their, I mean, their gradient have to be defined, okay? So I will, anyways, first explain about the entire process, and then we'll add more explanation for that, okay? So here, the thing we have to calculate is this. So df dx, df dy, and df dz. So we have to calculate the three gradient, okay? So this is same situation when we calculate the loss and differentiate this loss to each variables inside the graph, okay? So I will show you how we can calculate these three gradient. And first, there are some forward functions that can go in this direction. How the how to say the final f is represented by these initial variables. We can uh, define that forward function like this. So for example, the intermediate node Q, the output of this operator can be like this, okay? This is the formula obtained for this Q. So by adding these two variable, we can get the intermediate node Q. I agree with this. And also F is obtained by multiplying Q with Z. Okay, are you guys understanding this? Okay. First, I will calculate this. Okay, and this could be defined like this. Have you heard about chain rule before? Okay, so via chain rule, we can represent df dx as the multiplication of df dq and dq dx. Okay, and I will first get this df dq. Okay, and df dq can be obtained from this formula. So this is you already agree with this forward function. Okay, f can be obtained by multiplying these two variables, right? And we can apply dqd for left and right side. Okay. Then the right hand side becomes this. And when applying this to the right hand side, we can regard this as some constant and only can interpret this as the variable. Okay. And if we apply d dq to right hand side, it becomes z, right? And the z value now, the green value is meaning their current value, okay? So z is the -4 now, okay? So df dq, that is -4, right? Okay. And then we have to calculate dq dx, okay? And dq dx could be obtainable from here, okay? So if we apply d dx to left and right side of this function, then we can calculate d dxq is equal to 1 1 plus 0. So because this is variable, when applying this is constant. So if we differentiate constant, it becomes 0. And if we differentiate the first order variable, then it becomes 1. Okay. So this is 1 and this is minus 4. So df dx becomes minus 4. Okay. Are you guys following this? Okay. And you can do it for other things, but I will explain, I will calculate that by myself again for other gradient. So then we calculate that df dx is minus 4, okay, already. And then we have to calculate df dy, okay. It could be also divided by these two terms, okay. This is q, okay. df dq, we can reuse it from here, okay. And the thing we have to calculate is dq dy, okay. And now we can apply for here, instead of applying d dx, we can apply d dy to this formula to calculate this dq dy. Okay. And then you can see if we apply, sorry, d dy to this formula, then the left-hand side, it becomes dq dy, but the right-hand side, it becomes 0 plus 1, okay? It is again 1. So this is 1 again, and previously this part was minus 4. So we can see df dy is also minus 4, okay? And df dz, we have to also calculate df dz. Straight. And for that, we can use this, okay? So for that, we can apply d dz to this formula, okay? And the right-hand side, left-hand side, it becomes this, and the right-hand side, it regards z as variable, q as constant, so it becomes q. But you can see q is obtained from this, so and x and y, it is minus 2 and 5, so it is the summation of 2 and 5, so it becomes 3, okay? So df dz, that's 3, okay? So, I mean, I will upload this video in the web, okay? So you can re-watch this video if you are something missing, you think something is missing for you, okay? So you already see that previous lectures are uploaded in the Blackboard, okay? In the material, I wrote the link for previous lectures, especially for the lecture 2. Lecture 1, we did not record. For lecture 2, we recorded, and I already uploaded it in the Blackboard. The material, you can see the message. And for the lecture 3, I will upload it maybe by this week. So please rewatch this, okay? But I mean, this is very important thing to understand basics of the deep architecture, okay? How to calculate the deep gradient by hand is actually, I mean, I think this is the basic. So normally I raise this as the quiz 1, okay? So please practice this to understand, to properly understand what's going on here. Okay. Yes.
Where are the videos posted?
In the Blackboard, in the menu, where I upload this PDF. There if you go to the go to the lecture 2 now, then I type some link to the video. Okay. They are uploaded in the YouTube, so you can watch that following the link. Okay. 링크 찾았죠? 다 있죠? 네. Okay. So this is the lecture for lecture 3, and so but we have more time, so I will slightly introduce the lecture 4. Okay. Okay. So we already learned about the linear regression algorithm and also the MLP, okay, that can stack linear layers. Okay. MLP, sorry, that's called as deep architectures. Okay. And linear regressor, that is called as shallow architecture. So the difference is for the linear regressor, we just use one line of linear layer. Okay, that's same for SVM. SVM is also having just linear layer. Okay, so previously you may remember that using this exactly same formula for the SVM, we calculate their sign, output sign, and seeing their sign, if their values are positive, we regard it as the +1 label sample. And if their sign is negative, we classify the sample as the -1 class. Okay. So SVM, linear regressor, or other types of traditional machine learning algorithm, mostly they are using one linear layer. Okay. So in the SVM, you may remember we used the corner trick to map them to the nonlinear space. Okay, so that was the best trick that they can imagine. Okay, before, but if we stack more layers, you already see that from the examples we can make some network that can mimic this type of nonlinear functions. Okay. Actually, that's the merit of stacking multiple layers. So if we stack multiple layers, having deep architectures, by stacking multiple layers, we can deal with nonlinear functions. Okay, so that's one of the reasons why deep architectures are having good performance in real world. Okay, so in the real world, most of the data are not lying on this type of distribution that is linearly separable. Okay, so only the linear classifier they can deal with this type of data distribution well. Okay, but in reality, the data are not distributed in this way. Okay, always the data from the real world they are randomly distributed, and there are many cases the for the non-linear, cases. Okay, so in practice, deep architectures can, because they can model the nonlinear function, they can be better for real-world data. Okay, maybe I have to explain about this. So, but when stacking multiple layers, when we stack multiple layers, they are called as deep learning. Okay. When we stack multiple layers, if we can train their parameters, okay, as machine learning did, we call that as deep learning, okay? Deep architecture learning. That is called as deep learning. One condition which makes us to train that such deep architecture is this differentiability, okay? So, I mean, this is the essential condition that can make us to train the parameters of the entire deep architecture. So if those deep architectures are differentiable, we can train their parameters. Okay. So one essential condition for for having ability to train this deep architecture is that deep architecture have to be differentiable. Okay. So I will further explain about that. What exactly is the differentiability? Any differentiable layers could be in between these arbitrary input and output values. So I mean, this is I'm exemplifying the image classification task in this slide. So given RGB image, we want to predict their semantic labels. Okay. Or for different tasks, we can freely change these input and output values. Okay. So maybe we want to input some image, and even we want to make this deep architecture to generate some new image. Okay. I mean, any differentiable layers could be used for to map arbitrary input to arbitrary output. Okay. I mean, we can use gradient descent algorithm when given X and Y data, as we did before in PyTorch code, by providing many X and Y samples and making the deep architectures, we can train architectures, okay, to work as we desire, right? But one condition for doing that is that deep architecture have to be differentiable, okay? So you have to remember this, differentiable. But what is differentiability? Is actually explained here. So if they have these three rules, they are called as differentiable layers. Okay, so these two rules they have to have. The first one is dy dx, and the other one is dy d sector. Okay, I mean for this individual layer f, let's say their parameter is sector, then and also their y, we will define their output as y and their input as x, right? Then the firstly, they have to have this gradient, which means differentiation of their output respect to their input. Okay, that is dy dx. Okay, differentiation of output respect to the input. Okay, that's dy dx. And the other gradient we have to secure is this dy d sector, which means differentiation of the output respect to their parameters. Okay. If individual layers are having these two rules, they can define these two gradients. They are called as differentiable layers. Okay. So, I mean, having these two rules are essential conditions that they can be usable in the entire deep architectures. Okay. And why you have to have these two gradient is because we will have to update our parameter sector for entire network previously the parameters are called as W and B, but here we will call the parameters for entire architecture as sector. So the entire sector have to be updated using this gradient descent rule, right? And to do that, we have to calculate this, the differentiation of the final loss respect to individual layers parameter sector, okay? And if we can calculate this DLD sector for every parameters the individual layers are having, okay, then the entire deep architecture, regardless of their layer numbers, the entire deep architectures can be trained using this gradient descent. Okay. And by the chain rule, this DLD sector can be obtainable if the individual layers are having these two gradients. Okay. Are you guys understanding this? Okay. So, I mean, if you stack differentiable layers, okay, multiple times, if individual layers are having these two gradient, the entire network, deep network, can have these two gradient. Okay, and this DLD sector could be secured for the entire deep architecture. Okay, and their parameters can be learnable using this gradient descent formula, right? So that's why I'm telling that the entire deep architecture can be learnable. Their parameters can be learnable if their architectures their layers are differentiable. Okay? This is the only actually the condition. Okay? Any differentiable layers could be there in between this input and output. Okay, any differentiable layers could be here, any differentiable layer. But in the image domain, one of the successful differentiable architecture, deep architecture, is CNN, the convolutional neural network. So this is the abbreviation for convolutional neural network that is mainly having convolution operation as their main operator. Okay, but this convolution layer that is also differentiable. Their output is differentiable respect to their input, and their output is differentiable respect to their parameters. So they could be the main block to be stacked in the deep architecture. And in practice, the CNN is producing very good accuracy. Okay? So especially for the image classification, they are widely used in until early 2020s. Okay, but now the other architecture called as transformer that is also having differentiable operator in the middle. They are gradually replacing these CNNs because of their good accuracy. Okay, I mean any differentiable architecture could be in between input and output to map input to the output. Using gradient descent, we can train any differentiable layer. But in practice, when stacking deep architecture, when making deep architecture by stacking multiple convolutional layers, we observe that is producing very good accuracy. So because of that, we are using this CNN for a while. Okay. But after that, we realized that this transformer architecture having attention mechanism as the main operator, which is also the differentiable operator, we found that is producing better accuracy than the CNNs nowadays. So we are replacing CNNs with transformers now. And there could be another good architecture, which is differentiable and can be usable, to map input to the output. right? But so far, humans are not knowing better operator, better differentiable operator than the transformer. That's why we are using transformer as the main block. Okay. Anyways, later, maybe next week, next Monday, we will learn about what is the convolution operation and how they could be used in the CNN architectures. Okay. Okay. Thank you. Let's finish here for today. Thank you.